Hi, my name is Giulius Ruffa, and I work for the company Nelson. The company has decided to start this new program where we create step-by-step videos on heavily requested questions in our textbook. The first question that we will begin showing is question number 12 on page 84. This video will give a step-by-step explanation on how to do the following question. Part 1. Analyze the question. Here is a few seconds to read the question over. I have highlighted everything that will be important in this question. First thing highlighted are all the different planets' accelerations due to gravity. The next thing highlighted is the original equation for the function. Then I just highlighted what each variable means. So h is the height in meters, t is the time in seconds, and g is the planet's acceleration due to gravity, and k is the height in meters, which from the object is dropped. And the question is asking us what will be the, using derivatives, what will be the instantaneous rate of change of the height of the rock on each planet after 4 seconds. Part 2. What we should know. First, we should know what a derivative is. A derivative is a way to show the rate of change. And in this question, they're asking for the instantaneous rate of change. So the instantaneous rate of change is the rate of change that is measured at a single point on a consecutive curve. Now, how to take the derivative? There are multiple derivative rules. You have the constant rule, a linear rule, power function rule, power of a function rule, product rule, quotient rule, chain rule, and the constant multiple rule. This image is a breakdown on how to use on how each rule works. If you would like to see a more in-depth explanation of how each rule is used, please go to my other video linked in the description. But for this question, we'll only be using the power function rule and the constant rule, so those are the only two that I will explain in this video. So we know that this is our original function. And as said before, we'll be using the power function rule and the constant rule. So to break this up, left and right side kind of, the right side here we'll be using the constant rule, and on the left side here we'll be using the power rule. We know that, as I said before, the right side will be using the constant rule, and when you take the derivative of the constant, the number just actually goes away, so the k disappears. See, some of you might be thinking, but there's a g, so shouldn't that disappear too because it's a constant? No, the constant in this case is attached to the t, which is a variable, so it stays the same. So when applying the power rule, all you do is you take whatever the exponent of that variable is, you minus it by 1, so it would be 2 minus 1, and then you would bring the number of the variable down and multiply it by that variable, so end up becoming 2t to the power of 1. So now, before we start doing any calculations, let's actually show the original function on a graph and the derivative function. But for these, we need an actual g value, so we're going to be using the g value first, so 9.8. As you can see here, it shows 250 is the max it can go, and it shows the x intercepts. Now graphing the derivative. Questions asking in 4 seconds. So let's just get a rough idea where the instantaneous rate of change will be in 4 seconds. So as you can see, it will be around 30 now. Now I'm going to show you a step-by-step example on how to find the instantaneous rate of change for the Earth's acceleration due to gravity, then show a prediction on the rest of the planet. So from here on out, it's pretty easy. Use your derivative equation and plug in what we know. So we know that the Earth's acceleration due to gravity is 9.8 meters per second squared, and we want the instantaneous rate of change at 4 seconds. So t equals to 4 seconds. So first, let's write down the derivative equation that we found 2 steps ago, which is negative 0.5g 2t. Now let's plug in what we know. So we know our g, we know our t. Let's plug it in, and we just solve. I'll do that in a different color so you guys can see what other numbers I'm actually plugging in. So when you do this, attempt it on your own for the other planets, you know exactly what to do. Now you just solve. So you plug it all into your calculator, and you should get a number of about 39.2 meters per second. After 4 seconds, with the Earth's acceleration due to gravity, the rock has an instantaneous rate of change of 39.2 meters per second. If you guys get stuck and still can't figure out how to do the other planets, I just did here's a quick way of me doing them all. Derivatives are used all the time in the real world. In the world of business, functions are used to model the finances of a company. Derivatives of each function helps the business owner to determine optimum values, marginal profit, marginal cost. Using derivatives will allow business owner to know his minimal cost and maximum revenue very easily. Using derivatives will allow a company to show if they're going to make a profit or not. Overall, derivatives will basically show how successful your company could be. Now that concludes the video. Thank you for watching. I hope you have gained a better understanding on how to use derivatives to find also rate of change, and I hope this video was beneficial to you to understand and solve question 12 on page 84. I also hope that you enjoyed that little insight on using derivatives in everyday life and in a career. Now that's it for me, Giulius Ruffa. See you next time.